Hey everyone. Today we are doing our first lesson on vectors. For many of you guys who have taken a physics course or two physics courses, you'll have worked a lot with vectors, but some of you may have not. Whether you have or you haven't, everybody will learn something new in this lesson. And trust me, it ramps up pretty quickly with our work with vectors. So let's dive in. First, we have to actually talk about what a vector is, and at the same time, we have to talk about what a scalar is. So a scalar is a quantity that has magnitude only. So some examples of scalar quantities would be time, length, mass, area, volume, temperature, energy. So when I'm describing, how long it will be to dinner for our kids, 5 minutes. The length of something, 10 centimeters. My mass, 90 kilograms. It's all just a quantity and the units. There's no direction associated with these quantities. Distance and speed, distance, how far is it away? 100 kilometers. How fast was it going? 60 kilometers per hour. Those two quantities have vector counterparts, which we'll discuss right now. But a scalar has just magnitude only. A vector has magnitude and direction. So some examples of vectors, and a lot of these will be familiar from your physics courses. Position. So if I'm describing something's position, it's not enough to say, 5 meters away. Position indicates you need to describe very specifically, where is it? Because 5 meters can be anywhere around me. I would say 5 meters, straight ahead of me, or 5 meters ahead and to the left, something like that, right? Displacement is kind of a quantity that describes a change in position. Velocity, most of us, many textbooks, and I do this too, like in our grade 9 courses, speed, velocity, we just kind of interchange as the same thing. But once you start to take physics, you understand that speed and velocity actually mean two different things. Velocity is a change in displacement with respect to a change in time, and displacement's a vector. Velocity is a vector too. Speed is where you only concern about how fast you're going. Velocity is when you're concerned with how fast and the direction. Acceleration, force, momentum, those are all vectors too, and there's many more different quantities that are vectors. Those are just to name a few. We can represent vectors several different ways. Our first part of our vectors conversation for the next couple of weeks, we'll be talking about geometric vectors. So geometric is like an actual physical vector, like drawing an arrow on a page. Later on, we'll talk about algebraic vectors, which is conceptually talking about a vector maybe on a Cartesian plane or something. But for now, we're talking about a physical vector. I'm drawing it. I can see it on my page. This arrow represents a geometric vector. Some notation. We describe the tail of the vector to be kind of if you'd like to think about where it starts. If this vector described how something was moving, it would start at A and finish at B. I call this point the tip of the vector. You may also, in some resources, it may be called the head of a vector. But so this vector we could label as vector A, B. And when we're talking about a vector, we use this little half arrow vector sign above that. If we just had AB, that would just denote the line segment AB. AB with this vector symbol above it indicates this is a vector. Its direction is in the direction of A to B. And I can't stress this enough when we're drawing geometric vectors. You must have an arrow. The arrow indicates the direction. It's a common misconception. Hopefully you guys will break out of it quickly. That's a vector, but that little line I just drew, it doesn't have a direction. But now if I draw an arrow, I've assigned a direction to it. That vector has a length a magnitude, which I can measure, and it has a direction. But yeah, if you're not putting arrows on your vectors, then they don't have a direction and they're not really a vector. So that's important. Please draw little arrowheads. So that's one way to denote a vector. If a vector goes from between 2 points from A to B, you can call it vector AB. You can also just call vectors by usually a lowercase letter. It doesn't have to be all the time though. But a lot of times it's convenient just to go, hey, this is vector V. And we might just say, hey, that guy is vector V. So two ways we might describe vectors. You might just give a vector a name like V or U or W. Or you might describe it by where it starts and where it ends, like 2 points, A and B. The size or magnitude of a vector is denoted by what you guys are used to as the absolute value symbol. So when we want to know the length or the size of this vector, we use these symbols as well. So now you have to be careful in the context of if the argument of that is a vector, then it's the length of a vector. But if the argument of that is, say, a number like 2 or -3, then that's different. That's saying the absolute value of that number. Where here, this is the length of a vector. So that these vertical lines now can mean two things for you, but it just depends in the context you're working in. Are you working with vectors or are you working with numbers? So you shouldn't get confused. One note I'm going to squeeze in here as well, is that the size of a vector is always greater than or equal to 0. It's never negative. Keep that in mind, and that should make sense, right? If you're describing the length of a vector, like if you draw a vector on your piece of paper, you cannot take a ruler and measure that vector to have a negative length. That doesn't make sense. It's never negative. You can have a vector with 0 magnitude. It's called the 0 vector. We will talk about that in the upcoming days. But yeah, magnitudes of vectors are never negative. So if you get to doing some work in the future and you do find that a magnitude of a vector is negative, you should go back and check your work. I'll lastly say that right now, the direction of our geometric vectors is indicated by the arrow that we draw on our piece of paper. Later on, we might describe the direction of a vector using angles, using directions like on a compass, or even the Cartesian plane, but that's a bit farther down the road. A few more definitions. Vectors can be parallel, equivalent, and opposite. And these definitions are pretty intuitive. Parallel vectors have the same or opposite direction. So I'm going to draw, for example, here's two parallel vectors. I'll just call them U and V. U and V are parallel. They point in the same direction. But also, I draw a vector U, and I'm going to intentionally draw a vector V going the opposite way and make it even smaller. Those are parallel too. They run in the opposite direction. So they're basically like parallel lines, but they don't have to point in the same direction. They can be opposite directions. And a short way of saying two vectors are parallel is to use this notation here, U with like a /V. U is parallel to V. Non-examples, well, just draw any two vectors that kind of point off, something like that. Those would be examples of non-parallel vectors. I think I can move my handsome image to the bottom there. Great. Go on to opposite vectors. Anytime now. Screen, there we go. We're actually equivalent vectors next. There we go. Equivalent vectors are the same in every way. They're equivalent. They have the same magnitude and the same direction. So that's pretty easy to draw. Just draw like as best you can. I'm not getting a ruler out, and I don't expect you guys to right now. But those two vectors have the same direction and they're the same size. And for notation, we would just say that vector U equals vector V. This is important. It doesn't matter where those vectors are. I've drawn those two vectors in two different spots, but they are equal to each other. They are equivalent, same magnitude and direction. Non-examples. So I'll get two non-examples up here. So in the first case, you can see here that u and v are parallel, but they don't have the same magnitude or length, so they're not equivalent vectors. And here's a non-example. I'm being intentional here, where I've drawn these two vectors with the same magnitude or length, but they point in opposite directions. Those are not equivalent vectors. In fact, those are called opposite vectors. Opposite vectors have the same magnitude but opposite directions. So I'm just going to redraw that basically, u and v. And for notation, we would say that vector u equals negative vector v, which would also mean that vector v is equal to the negative of vector u. Non-examples, maybe for a non-example, you could do a couple. You could draw vectors that maybe have the same size but point off in different directions, and maybe have two vectors that have the same magnitude but the same direction. So those aren't opposite vectors. Those would be equivalent vectors. I do have a note here. So the notation there I have is if you're describing your vectors with just a letter. What if you were using describing a vector between 2 points? So let's say I have space to draw here, so I'm just going to draw. Here's a vector that goes from A to B. What would the opposite of vector AB be? If you want to think about that for a second, how would you state the opposite of vector AB? Well, the opposite vector has the same magnitude but different opposite direction. So the opposite of vector AB would be the vector that goes from B to A. The opposite of AB vector is BA. And that might be a useful property for us later on. We can actually say that BA is equal to the negative of AB, like so. And again, that might be a property that's useful for us later. A short exercise here. So there's a parallelogram with the four corners or vertices labeled A, B, C, D. Can you list 3 pairs of equal vectors and 3 pairs of opposite vectors? If you want to pause the video and try that, unpause when you're ready, or you can follow along with me right now. I might not necessarily write all the pairs of equal vectors. So let's start this way. The vector that goes from A to B. Well, that would be equivalent to the vector that goes from D to C because they would have the same direction, kind of going down and to the left, and the same length. You could cheese out another statement there. Well, then BA would also be equal to CD. Those two vectors would have the same length as the previous two. They just have the same direction up and right. And vector AD would be equal to BC. And I guess the last one would be, I might as well squeeze it on here. Maybe you said that DA is equal to CB. There's actually 4 pairs possible in that diagram. 3 pairs of opposite directions. There's many. I'm not sure I'm going to list them all. So again, you could cheese something out like AB is the negative of BA, or BA is the negative of AB. You could say that AD is the negative of CB. So if you think about that for a second, AD goes to the right, CB goes to the left, and they have the same length. They'd be opposite vectors. Maybe I'll do one more. I said AB was the opposite of BA. That's true, but AB is also the opposite of. AB goes down and left. CD goes up and right. So those are possible 3 pairs. Not an exhaustive list, but hopefully you get the idea. Let's talk about how we can describe the direction of a vector. So if you've taken physics, you probably use, not this one actually. We'll talk about that in a second. But there are two different ways to describe directions in terms of, north, east, west, and south. A true bearing, or azimuth bearing, is a compass measurement where the angle is measured from north in a clockwise direction. So you can see on our diagram here, we've got a true bearing of 40 degrees, 040. True bearings aren't usually expressed. They are expressed as 3-digit numbers, including zeros. So north is 000, east is 90, south is 180, west is 270, and I've drawn 040. That's 40 degrees clockwise from north. When you see the word bearing, when you're doing some work, it just means true bearing. So if you're given a direction in that way, a bearing of, it's from north counterclockwise. People that have taken physics might be more familiar with this method of stating direction. These are called quadrant bearings. It's a measurement always between 0 and 90, east or west of the north-south line. So in this diagram here, we've drawn north 23 degrees west, meaning from north, go 23 degrees to the west. A quadrant bearing always has 3 components. So direction it is measured from. So in this case, it was north, and then the angle 23 in the direction toward which it is measured. So north 23 degrees west, you can read as how I did, or it's 23 degrees west of north. Those are like just the same way to read that direction. South 20 degrees east is 20 degrees east of south. I can add that to my diagram here. South 20 degrees east means from south, go 20 degrees to the east. So it'd kind of be, my pen tool here, it would kind of be in the same, it'd almost be opposite to this guy. So from south, 20 degrees east, that would be that direction here. Some good talking points before I move on. There is more than one quadrant bearing for a vector. So north, let's actually talk about the bottom one and the top one. So south 20 degrees east. Well, in the same way, I could say that from east, I've moved 70 degrees to the south, and the original south 20 degrees east, those are the same thing. I personally don't care what you use. Sometimes people are kind of set in their ways and they always want to use north-south as the beginning one, but those two angles are the same thing. Maybe take a second and try to draw what the equivalent of north 23 degrees west is. Maybe use the diagram as a little hint. But you can also think of it as how many degrees north of west. So you can think of it as from west, 67 degrees to the north. That's the exact same direction. And again, I don't really care which one you use. One thing though, once we start describing directions, students want to, when we start doing questions involving, maybe forces and things like hanging from a ceiling and whatnot, up and down is not the same as north and south, right? Like up is up and down is down. North is a direction, like straight ahead or tomorrow, depending on where you're sitting, right? So up is not north. Just keep that in mind as we do problems later. We are going to do a couple of examples. So normally in the classroom, I'd get out the rulers, get out the protractors, and we'd make a scale diagram in these cases here. We're not going to here. We're just going to draw a rough sketch of these and then use trigonometry to determine the displacement. So this is also a little bit of a review, maybe in case you struggled a bit with the trig review that I posted last lesson. So let's dive in here. Mr. LeBlanc decides to ride to work one day. I just made these values up. These aren't the distances and directions to our school, but I say he rides 10 kilometers at a bearing of 020. So remember, So you can see, you don't have to think, is that a quadrant bearing or a true bearing? Like it's a true bearing because of the way it's 3 numbers. If it was a quadrant bearing, you'd have north, south, or whatever. So that's 20 degrees to north, so it's kind of going up that way. And then a bearing of 280 for the next leg. So remember 0, 90, 180. And again, this is not how you usually draw angles in the Cartesian plane. This is how you measure a bearing. So a bearing's always from north, 0, 0, 0, clockwise, 270. So a bearing of 280 is just above the east. If you would like to rewrite these, excuse me, as quadrant bearings, this would be north, 20 degrees east. And this guy here, you can think of as west, 10 degrees north. So I'm going to draw not a scale diagram here, but a diagram I'm going to use to solve my problem. So there is the first leg of the journey. So he rides 10 kilometers. You can see I've drawn an arrow indicating the direction there. Excuse me. At a direction of 020. And then he rides 5 kilometers at a bearing of 280. So 5 kilometers going this way. Now this diagram is not to scale. So that's 5 kilometers. And I'll put a little dash here, and it's 10 degrees above that horizontal. And what I'm interested in is his displacement. So his distance from home and the direction he winds up going in. So I'm going to draw kind of a vector representing where he starts and winds up. And our goal is to find the length of that vector and the direction. So right now, it's not, I'm just going to call that vector v. So right now, it's not really obvious whether, like the way I drew it, it appears he's going north and a bit west. That might not be true. That 5 kilometers might not be enough to get him back to straight north. So what we're going to do is we're going to find this entire angle in this triangle. And if it's more than 20, we'll know he's going to the west. If it's less than 20, we'll know he's going to the east. But we set up our problem is set up for us to use trigonometry. We have 2 sides in that triangle, but you will notice we actually don't have an angle in that triangle yet. But if you just want to follow through the logic with me here, you can see this 20 degrees is from that dashed line I drew north. And that intersects with this dashed line that I drew representing the west, east-west line. And north, south, and east-west intersect at a 90-degree angle, which would mean 20, 90, that this little bit here is 70, and so the entire angle is 80 degrees. So if you want to make that a lot bigger on your diagram, or if you want to rewind the video and just walk through that logic again, I know you guys did problems like that in your grade 10 course, so you should have experience with that kind of reasoning out directions. But yeah, so we reason out that the angle between his 2 legs of his journey is 80 degrees. And now we can solve the problem. To find the length of that resulting vector, his distance from home, we have to use the cosine law. So you guys have been using this for several years, so I might just go into a pretty quick calculation and kind of not show a lot of steps here. So the cosine law is the magnitude of that side squared is the square of the other 2 sides. So it's like a modified Pythagorean theorem, so eventually it will be rooting. So it's the root of our 2 other sides squared and added together, minus 2 times the product of those 2 sides, and the cosine of the angle between them, which we found is 80 degrees. You know, in my grade 10 course, I might show a lot of extra steps setting that up, but you guys have been using the cosine law for 3 years now. It should be just a tool you have in your toolbox. And I just got caught on this. Make sure your calculator is in degree mode, because I know from our last unit with trig functions, we did some stuff in radians. So make sure you're back in degree mode. So 100 plus 25 minus, that'd be 100 times cos 80. Don't forget to square root. So I got that the magnitude of this vector is about, I'm going to keep 2 decimal places of accuracy, 10.37 kilometers. So, if I drew a scale diagram here, and maybe you did this at home and tried to measure all your angles perfectly. If you, let's say, said that 1 centimeter on your page was 1 kilometer, and you drew a 10 centimeter vector, a 5 centimeter, and drew everything to scale, if you measured the length of from where you start to where you finish, it would have been about 10.37 centimeters or 10.4 centimeters. But we just solved it relatively accurately. That's the distance, though. We want the displacement. Remember, displacement is a vector, so we need the direction too. So let's go about finding this angle. So right now, it is pretty obvious that angle is going to be acute. So we don't have to worry about any ambiguous cases with the sine law. So you have 2 options here. It is pretty clear that angle is acute, so you could just use the sine law. So sine theta over its opposite side 5 equals the sine of, we have 80 degrees and its opposite side 10.37. You can set it up that way and get your value for theta. Or if you weren't sure whether, because if that angle was obtuse, the sine law would fail. You guys learned that in your grade 11 course. You do have all 3 sides though, so you could use the cosine law. So the cosine of that angle, theta, would be 2 sides that kind of sandwich it, 10 squared plus 10.37 squared minus the opposite side over 2 times 10 times 10.37. We have more information than we need to find that angle, but why don't you try getting that angle 2 ways? So I'm going to do that as well right now. I'm going to do 5 times sine 80 and divide by 10.37. Maybe I'll show an extra step here too, actually. I get the sine of the angle is about 0.4748 inverse sine. So I've got about around to 28.3 degrees. If you use the cosine law, we should get the same answer. Plus 10.37 squared minus 25 divided by 20 divided by 10.37. So I'll show a step here too. I get the cosine is about 0.8801. And if I didn't do this ahead of time, so hopefully I get it right. Expecting the same answer. Yeah, I do get 28.3. Kept a lot of accuracy. You get the same both ways. But I'll just stress one more time, and this is something you've learned. The cosine law, because cosine using the cast rule, C-A-S-T. Cosine is positive in the all quadrant and negative in the sine quadrant. So you'll get a unique value, whether it just depends on whether you get the cosine of positive or negative. You'll get one answer. However, the sine law, the sine ratio is positive in the all quadrant and the sine quadrant. So if you get a positive value for sine, ultimately you don't know whether your angle is acute in the all quadrant or obtuse in the sine quadrant. We're relatively sure it's acute, but if you weren't sure, you'd have to use the cosine law to make sure that you get the right angle. But yeah, we get 28.3 degrees either way. Just be careful of the ambiguous case with the sine law. Let's try another problem. So in this example, everything here, we have several legs of the journey, 3 kilometers north, 6 east, 5 south, 2 east. So again, normally with my class, I would draw a scale diagram here. But let's just draw what's going on. So I'll make sure I have some room. So 3 kilometers north, let's say, and then 6 kilometers to the east. So everything forming right angle triangles here. 5 kilometers south, something like so, and then 2 kilometers east. Now, you don't have to do 3 different trig problems, like find the distance from here and then find the new distance, like going down. That would take a long time. this question, everything's purely in terms of north and south. So hopefully you guys are convinced, like if ultimately he rides 3 kilometers north and then 5 kilometers south, and the other legs are just east, hopefully you guys will be convinced like that and overall he'll be going 2 kilometers south. And then he goes 6 east, 2 east. Overall, he'll be traveling 8 kilometers east. So we can make this problem into a simpler problem like so. And we are interested in what is the length of that vector, the displacement, and what is the direction. And before I get too deep into this one, actually, we didn't actually answer the question from the last time. We found the distance, but what was this change of position from home? So we found that this angle was 28.3 degrees. That means that for vector v, and I'll just draw this in green just to finish this up here. Vector v was, our distance was 10.37 kilometers. And so what's our bearing? So the entire angle is 28.3 degrees. 20 degrees of that is to the right of north. That means 8.3 degrees is to the left of north. And what bearing is that? That's 8.3 less than 360. So we'll just go to the nearest degree. So 8 less than 360 is 352. It's at a bearing of 352 degrees. So just wrapping that one up. The next question here, because we have the distances in northeast, southeast, my anticipation is that you would use a quadrant bearing for when you're done here. So you guys can find, the way I've drawn it, we're finding the angle east of south. If you want to do this on your own and check in a bit, unpause the video, you can, or you can follow along with me. This one, the math is pretty quick because it's a right angle triangle we're working with. So we're just using Pythagorean theorem. The size of that displacement vector be the root of 2 squared plus 8 squared, which is exactly the root of 68, but let's just get an approximate value. I'm going to say 8.25 kilometers. And the direction, so I can just use the tan ratio here, and I'll be doing the inverse tan. So theta equals inverse tan of 8 over 2. Opposite over adjacent. Shift tan of 4, pretty much 76 degrees. And so we can say in this problem that Mr. LeBlanc's displacement, his net displacement, he finishes 8.25 kilometers from home. Which direction is he in? Well, this direction is in the southeasterly direction, from south 76 degrees east. Now, if you did this problem, drawing it the other way, east and then south, you might have this answer. You might have east 14 degrees south, which is okay too. It's the same direction. All right, guys. So in this video, we've introduced some terminology for our vectors unit, and we're working with geometric vectors right now. A physical vector we're drawing on a page. We've reviewed some trig tools for kind of combining vectors together. What's left for you guys to do is a bit of practice. I've got a PDF on Brightspace for you guys to try. Now, one thing, I'm not a fan of texts that do this. But you might come across this kind of language. Maybe describing like the direction of the wind. You might see 100 kilometers per hour from a bearing of, I don't know, let's just say 100 degrees, like so. So 100 degrees, we've talked about this. From 0, there's 90, it's from north. So 100 degrees is kind of like here. Here's 100 degrees. So if a question is saying it's 100 kilometers per hour from a bearing of 100, that means it's coming from here and actually moving up and to the left. That means the wind is actually blowing not in a southeasterly direction. It's actually blowing in a northwesterly direction. So keep that in mind. Look for that language in these problems if it says from a bearing of, compared to, you know, to or at a bearing or to a bearing. So, you know, just be warned, it does pop up now and then in the specific resource. That's it from me. Please let me know if you need anything. Have a great day, guys, and we'll see you soon.